let's try to show an example of how to solve a partial differential equation numerically. We'll try to do the numerical Laplace equation because easy. And the general form of that is something like this, as you saw on the blackboard like 15 minutes ago. Okay, so what do we do if we want to solve this numerically? Well, we have to make a numerical grid to begin with. Let me cheat a bit. So you have your grid here, y direction, x direction, and you divide it into nodes. Like so. So you're trying to solve the numerical Laplace on or inside this area here. See, we have y0 equals c y equals d. Of course, you can shift this grid as much as you want. A and x and b. And since this is a finite difference, the difference between each point should be, well, finite and not changing. You also have the finite element method, where I suppose the number of elements is constant. But we will look at, well, to begin with anyway, we will look at finite difference methods. So here I define that the distance grid point in the x direction is h, and the distance between each grid point in the y direction, what did I? K. K, like so. So this is a so-called finite difference method, or FD. So that each of these nodes xi is divided into a start plus a number times h, which is distance between node, and y of j equals c times j k. So we have n x points, I equals 1, 0, 1, 2, all the way to n 1 for j, all the way from 0, because 0 gives us all the way over there, 1, 2, minus 1. So this is n points, this is m points. Start counting 0. That's a grid. You've seen similar before, those in mathematics? Yeah. Good. And then I will use u of xi, yj. I would write this as ij. Okay, so see, there can be a bit of confusion because I also have u xx here, but here I have ij. So you're supposed to figure out what it is out of context, I'm afraid. So this is the value u as some kind of point ij. So u 0, 0 is going to be this point. U 1, 0 is going to be this point. U 2, 2, 0, 1, 2 here, and 0, 1, 2, 2, 2, 2, 0, for instance, in this stencil. Okay, so how do I solve this equation then? X plus y. Okay, so please don't be confused. Tell me if you're confused. So this means a differentiation. When it's xx, when it's ij, it's a position. It's an evaluation of u at a position. So for instance, we can say that uxx, we can use a central differentiation operator. That is uxx, same as the 0 twice in the x direction. Have an x here, for instance, u, and we have this in our notes from before. This is ui 1 j minus I j plus ui minus 1 j over squared. And then again here we get an error term, h squared 12 dx 4 I y j. Like this. I is somewhere between xi minus 1 and xi. The error term. Like so. And again, similar for yy. E0 in the y direction. U. That's u I j plus 1 minus u I j plus I j. Okay. Squared. 1 j squared 12 dy for u xi eta j, or some kind of eta and yi 1 yi plus 1. Well, that was fairly straightforward. And again, if you want more accuracy, you could have a larger differentiation operator. We only used, well, one step. So, neighboring points. You could also have used a forward operator or a backwards operator. That depends on the problem. But since we are working in space, the central one is better. And you also see that we will have some problems in the corners, where we get back to this. Okay, and usually you have the h's case, unless you have some reason to do it. Then we can put these two together. Here, that's what we're solving. And we get u I plus 1 j minus ij 1 j over h plus I j 1 minus 2 j plus I j minus 1. Okay. Well, say that we're going to assume that h equals k. Not. We don't have any reason not to do it right now. But in a general sense, you could have a different spacing between them. Just make everything easier when you have the spacing. So this is going to be 0. Or actually the error term we have, which is squared. No. dx. Or yes, it should. It should. Did I? Yeah, I forgot it over here. It's there, so it should be h squared. Thank you. It's I y j plus dy. It's I j. Thing is here, we can solve this for ij. So if you just assume that the error is 0, I mean, you can't calculate the error, but in this case, yes, let's just assume it's not 0. We can solve for ui. This Laplace equation at ui plus 1 j u plus 1. Okay. I'm just ordering all of the I, j, 1, j minus 1, for I, j. It should be 0. And then let's solve. So here, this is basically the same, this one. Only I ignore the error. That means that we can actually figure out what okay, then written. So I can solve this equation for this, for ij. What we can say, so that should be trivial to solve for uij. When we do that, we see that we get some kind of stencil, like a cross. We have ui minus 1j over here. This side we have ui 1j, ui j minus 1. Here ui j plus 1. Then here for I j. And this is called the stencil of this equation. So And the reason why I haven't included the h's here is because they can be easily kind of multiplied away. If you just take this equation and multiply with h on both sides, well, also falls off here, and 0 times h squared is 0. But we're still missing something. We can't solve this. I mean, the stencil, we can place it on our graph, so it's fine if we do it here. Actually, it's not fine anywhere. Anyway, assume that we have this value. So we can place it here. So in order to calculate u22, we need these 4 values. And we don't. All of them. Up here, we need some kind of boundary condition. So we have to define them. So that is, to the left side, call this GL for left. Right side, G right. Top side, GT. And bottom side, B. We also need these in order to solve this equation. You would also need this if you wanted to solve it analytically. So this is the boundary conditions. G, L, R, E, and B, B. These are boundary conditions. Or BCs, boundary conditions. So we have defined that u of 0, j, GL, 0, yj, or 0, j, minus 1. For instance, so that's the first one. So what does this mean? Well, u0, that's along this line, and all the yj's, that's points, goes here. This is basically just formalisms. U of I m, that's going to be this side. No, sorry, that's going to be this side. That's u I m. That's t x I m 0 I 1. U of j and this one, gr. Gr of y, j, and the row. That's bottom one, gb of xi, y, 0, 0, minus I minus 1. So if you assume that we know these boundary conditions, here we get a system of equations, in this case linear, and Words. Get. Two. Just two equations. With n minus 2 minus 2 unknowns. Meaning that we can actually solve this system. So I have plenty of time for example. There are also examples of how to solve this on GitHub. And there are many ways to solve it. Either use conjugate gradient, directly solve it, descent. So, an example here. We get the grid C at P1, 2.3, 4.5, 0.6, 7.9, which we're going to solve on a grid. I should have. So this is inside, and then we know the value along these points on the outside. L value. And you see that the corner points here, this one, and this one, they should all coincide. They should give the same number. So the functions we have, the bottom and the left side is just 0, meaning that you have 0 along this line and 0 along this line. And for the top one, get of x, y is 5. Okay, yeah, I'll get to the just later. This is grid times x, and the g right one 0.5, and y equals y. So again, the grid spacing h. So here goes to 5 in the x direction. Here it's 5 y direction. This is a plane grid. And we say that is one in order to fit all these points by this area. Okay, so what do we have to do next? Again, I should point out explicitly we are solving the Laplace equation, namely 0. That's the one we're solving on this case here. Okay, so I have to create a vector with all of our points. Not a matrix, but a vector. Equals 1, yep, 1, P2, und so weiter, all the way to then we can take a look at some of the equations. We'll see that there's a system to them. Seven, eight, nine. Oh, my bad. I can't count. It's supposed to be 9, of course. Good. Okay, so if you all remember this equation, we can write all of these points as numbers of this. So for E1, namely this point over here, we get the equation to the L of 0, 3.8 plus top, the L, this point, the top, this point, to there, and we also 4. G top of 1/8 or 8 plus P4 minus 1 equals 0. And do you see the similarity between that equation and this? On the right-hand side? P ui plus 1. That's P2. That's this one. And then you have u, is it I minus 1? Yes, that's this point. Then we have plus ui j plus 1, that should be this point, and then we have ui j minus 1, which is the point down here. So then we have applied our stencil here. And then ui j as p1. We can solve this for p1 if we know these two. So we need equations for p2 and p4 as well. But rewrite this slightly. 4 p1 p2 plus p4 plus minus L 0 3.8 GT 1 4 off, what is known as this equals 5. If we do it similarly for P2, we get the equation minus 4P2 plus P1 plus P3 plus P5 minus of T, no, U8, 4 half minus 50, and I'll do one more, P3, 4, 3 plus P2 plus P6. And then we have for this in the middle It's only points. Five, so there's a system here which we get to store them. P5 plus P4 to the left of it plus 2 below it, no, above it, plus P6 to the right of it plus P8 below it equals 0. Okay, so we can do this for all of the equations. No, for all of the points in this grid, we can have some equations for it. Or we could write this as a matrix. I've, yes, sorry. Did I skip it? No, I didn't. Minus GT, 3, 8, 4, 8, BR, 4, 3 8, and we end up with minus 150. Yeah, my bad. But there's an easy way to summarize all of these equations. Matrix. So we see, first one, we have minus 4 of P1. Let's see, that's 4. Minus 4 of P1. We have 1 of P2. We have 0 of P3. And we have 1 of P4. For the next one, we have this one. We have 1 P1 minus 4, 2, have 1 P3, 0 P4, but we have P5. Okay, so that's good. And then for P3, well, we have, yep. Yes, they should. This is just zeros. I will fill them out later. Next one, 0 ones, 1 2, yes, 1 2, minus 4 3s, and well, we actually skip 1, and 2, and we end up over there. Again, 1 0 0 4 0 1. And then you see we have this pattern repeat. If you want all the zeros, then we have for 1 2 3 4 5 6 8 fill them out. But you see these bands continue. So this minus 4, minus 4, minus 4 continues, except there are some breaks in it when you are at the edges. Let's see, it's on line 4, 4, this one, this one. So that's when you are in the edges. So you see here, 1, 2, so this is for P3. P3 is this point here. You don't have anything to the right of it. And the same when you go to P4, you don't have anything. Oh, well, you have this number to the left of it. That's why you have breaks in the bands. And if I don't remember correctly, so, and then these bands will just continue downwards. So that's your A matrix. If you're diligent, you can finish the construction of this 9 by 9 matrix. P1, 2, P3, and P9. Big matrices. And then we need all of these numbers on the right hand side. 5, 50, minus 50, 0, 0, minus 50, 0, minus 5. A matrix and P kind of G or B. So let's see if we can actually solve this. So you see this is so sorry for not finishing the matrix. I would have gotten it wrong because there are so many numbers, but I show you how to construct it. To construct the general form, yes. But I mean, then it's fine if you just do this, then stop there, and then say that, oh, these bands repeat down there, this band repeats down there, and this band repeats down there. You're expected to do this on the exam. If you go to the previous 3 or 4 exams, there have been questions. I think there's not the first week, but there will be. I think it's for a month. We can take a look at the. You're asking. Look. Nah, you don't have to do all the exercises. So this is the plan. So this document should be available to you as well. So you have over 4 weeks to finish the project, and these exercises aren't. Well, these shouldn't be too difficult. I also tell the TAs to be kind of easy on you on grading them, but focus on the project. This. No. No, it's not possible. I'm away also, presenting at a conference. So yeah, it's all here. 10 days, between the 12th and 22nd. But I will be available on Slack, so in a staggered time. But how to construct this matrix? And this is, of course, available on Blackboard Slack. And I will try to update it. This isn't the latest version, so I will update it. Okay. So this is basically the example we've done right now. I would solve. So this is solving it in a very straightforward fashion. No, it's the direct one. So I've said that we have 3 inner nodes on the x-axis, or that is these 3, and then you have these 3. Calling them inner nodes on the axis, I could have maybe worded it a bit better. Okay, and then I say that E is just a vector of 1s, and n, that's the dimensions, that's n here, 9. So this is creating a vector of just 9 ones. And the same with D. Then I say let's solve 0.